Hello, Mr. Sutton, bringing you the IM384 Part 1 homework solutions on independent and dependent probability. For this problem, we have to figure out if these are independent or dependent and find the probability. So our sock drawer has 4 white socks, 6 brown and 6 black, and we want the probability that we randomly pick 2 socks and get a matching pair of black socks. All right, so if you're picking 2 socks out of there, presumably you're not putting one of the socks back after you pick it out. So this would be dependent because what you do when you get that first sock is going to affect the outcomes that you could get from picking that second sock. So now the probability of getting a black sock followed by a black sock, well, how many socks are there overall? We have 4 plus 6 plus 6, that's 16 overall. So that's the overall sample size to begin with, and then, or the sample space rather, and then for black socks, they said there were 6 of those. So we have 6 over 16 for that first black sock. Now after you pick that first black sock, your sample space gets reduced a little bit because now you have 1 less sock. So now you're down to 15 socks to choose from. And you've also affected the number of black socks as well. You have less desirable outcomes now. Instead of 6 black socks, now you're down to 5 black socks. Now at this point, we can reduce this a little bit. This 5 over 15, well actually let's do the 6 over 16 first. So that can reduce to 3 over 8, and 5/15, that's really 1/3. These 3's can then cancel. I guess I could have canceled a little earlier, but whatever. We end up with then 1 over 8 for our probability. For this situation, we have a basket with 6 apples and 6 peaches. And then 3 times we're randomly picking a piece of fruit, returning it, and mixing the fruit. And we want the probability, and also whether this is independent or dependent, as to whether all 3 times the fruit is an apple. So if I'm picking the fruit out and then returning it, this is the key here, returning it to the basket, then these are independent events. What I do on my first pick has nothing to do with the other picks because I'm just putting the fruit back every time I pick something. So if we want the probability of so this, again, is independent. Now, if we want the probability of an apple followed by an apple followed by another apple, I know I love my apples. So the first apple then, well, there's 12 pieces of fruit overall, 6 apples and 6 peaches. And in terms of desirable outcomes, 6 of those are what we want, the apples. So we have a 6/12 chance that first time around of getting an apple. Now, after we put that apple back and pick again, we still have 12 pieces of fruit and 6 apples. So we just multiply by 6 over 12. And then we put that back and we still have 6 pieces of 6 apples and 12 pieces of fruit. So we again multiply by 6 over 12. Now to make our lives a little easier, not have to use a calculator here, we can reduce each one of these to 1 over 2. And if I've got 1/2 times 1/2 times 1/2, that's just going to be 1 over 8. So there's our chances of getting 3 apples with replacing. On this one, we want to figure out if we have an independent or dependent event sequence here, and then find the probability. So our situation is we're flipping a coin 4 times and then rolling a 6-sided die just once. And we're talking about a coin landing heads up every time, so all 4 times, and then the die showing a 3. All right, so we want the probable, first off, is it independent or dependent? So when you flip the coin, each time you flip the coin, it doesn't really affect your future coin tosses because, you know, flipping, you can get heads or tails multiple times. They don't get used up. And then whatever you do with the coin has absolutely nothing to do with what you're going to get from the die. So these are all independent events. So now let's talk about the probability of 4 heads and a 3. So the first head, you have a 1 in 2 chance of getting that. And then you have a 1 in 2 chance for the next one, and the next one, and the next one, right? These are all independent, so it's just a 1/2 chance every time. And then for that 3, well, you have 6 total possibilities because it's a 6-sided die, and 3 is just one of those. So that's a 1 in 6 chance. So now multiplying all of this together, we've got, let's see, 2 times 2 times 2 times 2, that's 16. Times 6 is 96, so then that's going to be 1 over 96. For this one, we want to figure out independent versus dependent and the probability for a cooler containing 10 bottles of sports drink. We've got 5 lemon, lime, and 5 orange flavored. Let's say you randomly grab a bottle, give it to your friend, and then grab a bottle for yourself. And we want the probability that your friend and you both get lemon lime. Okay, so independent or dependent? Well, the drink you pick and randomly give to your friend, that's going to affect the drinks that you then have to choose from for yourself. So since earlier events affect later events, these are dependent events. So now let's talk about the probability of getting lemon lime twice. So the first time around, you have 10 bottles, so that's your total possibilities, and out of those, 5 are lemon lime. So we'll say 5 over 10 is the probability of getting that first lemon lime that you give to your friend. Now let's talk about you. Well, once you pick a bottle, any bottle out of there, that drops your total possibilities to 9. Now there's 9 bottles left to choose from. And if one of them just happened to, if the one you got was a lemon lime, well, now there's no longer 5 lemon limes, there's only 4 left that you could get. So we have a 4 over 9 chance for that second time around. And then let's just reduce this a little bit before we multiply it through. So we can reduce the 5 and the 10. That's going to be 1/2 times 4 over 9. And then we can reduce the 2 and the 4. So that's going to give us a 2 in the numerator. So then when all is said and done, in the numerator we've got a 2. 1 times 2 is 2. And down below we've got 9. So 2/9 chance. For this problem, we want to figure out independent versus dependent and the probability. Our situation, we have a bag with 8 red marbles and 3 blues. And then we have another bag with 5 greens and 4 yellows. So 2 different bags with different types of marbles in them. And then you randomly pick 1 marble from each bag, and we want to know the probability that 1 marble is blue and the other is yellow. So independent or dependent? Well, since you're picking a marble from each bag, what you pick from one bag has no effect on what you get to pick from the other bag. So these are independent events. They have nothing to do with each other. Now, in terms of our probability of a blue and a yellow, let's talk about the blue first. In the bag with the blue marbles, we had 8 plus 3 is 11 overall marbles in that bag. So we're going to have something over 11 for the probability of blue. Now, how many blues were in that bag? Well, they said 3 blues were in there. So 3/11 is your chances of getting a blue. Now, for the other bag with the yellow marbles in it, that bag not only had 4 yellow marbles, but 5 green ones. So that's a total of 9 marbles in that bag. So we have 9 for our total possibilities, and 4 are yellow. So 4 out of 9 is what we're looking for. All right, so before we multiply this, let's reduce a little bit. The 3 and the 9 can reduce to give us a 3 in the denominator. And it looks like that's it for reducing. So multiplying this through, we have a 4 left over in the numerator, and 11 times 3 gives us 33 for our denominator. For this situation, we've got 4 nickels, 3 dimes, and 5 quarters in our pocket. We randomly pick 3 of them and place them on a counter, and we're talking about the probability and also whether these are independent or dependent events, that the first 2 coins are dimes and the third is a quarter. Well, once you've picked a coin out of your pocket, you're not putting it back in your pocket, right? You're picking 3 coins and placing them on the counter, all 3 of them. So there's no replacing, which means that these are going to be dependent events because the coins that you pick the first and the second time are going to affect what you can get on that third pick. So now that we've established that, what is the probability of getting 2 dimes followed by a quarter? So the probability of the first dime, well, let's take a look at our total possibilities. There's 4 nickels, 3 dimes, and 5 quarters. 4 plus 3 is 7, plus 5 is 12, so that's 12 total possibilities for that first dime, but only 3 of those are dimes. So we have a 3 out of 12 chance of getting a dime the first time around. How about the second time around? Well, the second time around, there's 1 less coin because you just picked one and put it on the table, or the counter. So that's 11 coins left for the total possibilities. Not only that, but if you just picked a dime, that means there's now not 3, but 2 dimes left for that second time around. And then we go to the quarter, having already picked these 2 dimes. So that means there's 1 less coin again in our pocket. So now we're down to 10 coins for our total possibilities. But since you're picking a quarter rather than a dime, the number of quarters is what it was in the beginning. you started with 5 quarters and you didn't pick any, so you still have 5 quarters. So we'll put a 5 up here. Now let's reduce a little bit. So the 3 and the 12, we can reduce that to 1 over 4. 5 and 10 is another easy one. That's going to be 1 over 2. And then while we're at it, this 2 and the 2 we just got by reducing can also just completely cancel. So now, since everything in the numerator is gone, we multiply all these invisible 1s to get a 1 in our final numerator. And down here we have, let's see, 4 times 11 is 44, and it looks like that's it. Everything else is canceled. So 1/44 is our probability. On this one, we have a box of chocolates with 4 milk chocolates, 5 dark and 5 white. And then we randomly select and eat 3 chocolates. So we're talking about whether these are independent or dependent events first. So if you're randomly selecting and eating 3 chocolates, well, you've heard the expression, you can't have your cake and eat it too. It applies to chocolate as well. If you're eating the chocolates, then you're not replacing them and choosing the same chocolate again. So these are very dependent events. The chocolate that you pick and eat the first time around is going to affect what you can pick and eat the second and the third times. So now the probability we're looking for is that the first piece is milk, the second is dark, and the third is white chocolate. So we want milk, followed by dark, followed by white. All right, well, let's talk about the probability of the milk chocolates first. And to do that, we need to know how many chocolates there are total for our total possibilities. So we had 4 plus 5 plus another 5. That's going to be 14 for our total possibilities. And of those, only 4 are milk chocolate. So we have a 4 out of 14 chance that first time around getting a milk chocolate. Now, once we've selected that milk chocolate, now we're down to 13 chocolates, right? Because we just ate it. So that's 13 for the total possibilities when we're trying to pick a dark chocolate. But we haven't eaten any of the dark chocolates yet, so there's still 5 of those hanging around in our numerator. Next, now that we've eaten a dark chocolate and a milk chocolate, there's only 12 chocolates left. This problem's getting tastier by the moment, right? But again, since we haven't eaten this last one, we haven't eaten any white chocolates yet, that means there are still 5 white chocolates for us to choose from. It is only the outcomes, total outcomes that went down, not the desirable outcomes. All right, so we've got all this established here. Let's reduce a little bit, and then we'll multiply. So let's see here. There's a few ways we could do this. I'm going to reduce the 4 and the 12 because then I can completely cancel the 4. So that gives me a 1 up there and a 3 down here. And it doesn't look like anything else is going away. So we have 5 times 5 in the numerator. That's 25. And 14 times 13 times 3 in the denominator, which I will do on the calculator. And it looks like that's going to come out to 546. And since we've already reduced everything else we could, this is as good as it's going to get. So for this set of events here, we want to know if these are independent or dependent and then get the probability. So the event itself is flipping a coin and rolling a fair 6-sided die. Well, the coin and the die have nothing to do with each other. Whatever you get with your coin toss does not affect the dice roll. So these are independent events then. And then we want to find the probability that our coin lands heads up and the die shows an even number. So heads up and even is what we're looking for. So the probability of getting a head, just flipping that coin once, is just 1 out of 2. The probability of getting an even number, well, half the numbers on the die are even and half are odd. So you have a 1/2 chance of getting an even number. And then just multiplying across, we end up with 1 over 4.